Welcome to Lesson 12B, Control Velocity. Now we're going to talk about control velocity, which is different from capture velocity. We'll define it, and then we'll talk about how to use it. Let's define control velocity. I have it here. It's a design parameter used in hood design, just like capture velocity was. But this is for the capture of vapors or mists, not of particles. And it's from evaporation from free surfaces. The difference between vapor and mist, a vapor is a gas and a mist is tiny droplets. I want to first do a comparison between capture velocity and control velocity. First of all, the symbol for capture velocity was V sub c, and the symbol for control velocity is none. It's a design parameter, so it's not a physical property. It's not really a velocity. It has units of velocity, but it's just a design parameter. What do you match? You match VC, capture velocity when we're talking about particles, to the local U of the hood. Whereas with control velocity, you match the control velocity of the process to the control velocity of the hood. And then we use it for capture velocity for particles and control velocity for mist or vapor. So let me go through the procedure and then I'll do an example because you'll learn best by example. Table 6.2, the top of it, is used to determine something called the hazard potential, the letter A, B, C, or D. This is based on the chemical properties like PEL, flash point, etc. And you always choose the worst case. What I mean by that is you choose the most hazardous. In other words, we're being conservative. I'd rather suck out too much air than not enough air, so we choose the worst case, and it turns out that the lower letter equal more hazardous. If you have something with a very low PEL, that will have a low hazard like A or B. If it's a very high PEL, we're not as concerned about it, then you might have a C or a D. If you have conflicting values depending on PEL or flash point, etc., you would pick the lower letter. So always choose the worst case, which is the lower letter. We have step 2, that same table, 6.2, but the bottom of it, to determine what we call the rate of contaminant evolution. And that's a number, 1, 2, 3, or 4. So we got a letter and a number. And this is based on the liquid. Remember, this is liquids evaporating from a tank. So you're going to have a liquid temperature, a boiling temperature, and a few other parameters. Again, choose the most hazardous number. The lower the number, the more hazardous. Once you have the letter and the number, you just combine them. So you'll see things like A1, B3, C2, etc. Step 3, now use table 6.3 to determine this control velocity in feet per minute. I just wanted to make a comment here. A1 is the most hazardous, and D4 would be the least hazardous. Control velocity is based on the class. By the way, this is called the class when you combine the letter and the number, and type of hood. And then finally, step 4, use table 6.4 to calculate the required hood volume flow rate. And what you actually look up on that table is Q over A in CFM per foot squared. And then from that, you find Q equal Q over A times A. And this area, A, is the tank surface area of the liquid. This is Q of the hood. How much flow rate do you have to suck out of this thing? I'm going to do an example, which is the same one in the text, so you can look in the text for a little more detail. You're dipping these copper plates into a chemical bath, which has sulfuric acid to clean them. We have the dimensions of the tank, the bath temperature, and it's an acid mist. The liquid mixture boils at 225. Obviously, T boiling is greater than T itself because the temperature can't exceed the boiling temperature. We're going to do 2 different cases. Case A, tank against a room wall and a lateral exhaust on one side, versus a freestanding tank, this is case B, with lateral exhausts on both long sides of the tank. So there's a W and there's an L, so this diagram shows you which is considered W. It doesn't mean that W has to be less than L or vice versa. And both these cases are the same temperature and the same boiling temperature because it's the same liquid. So same process, we just have 2 different tanks and kind of figure out which one's better. So step 1 was to look at the hazard potential. That's that letter. So I look up the PEL for the sulfuric acid mist, 1 milligram per meter cubed. I also look up the flash point. It's a temperature at which if there's a spark, these mists would potentially explode. And I really couldn't find any. So in that case, we cannot use that. So we're going to have to base this just on the PEL. From table 6.2, the hazard potential is B. Here's the table. First of all, is it a vapor or is it a mist? It's a mist, and the units are milligram per meter cubed. That falls in here.
But sir, what if the PEL were, say, 1.05? What would we do then?
The answer is you're never going to have PELs to 3 digits.
I see. Thank you, sir.
We don't have a flash point. It probably was not an important parameter, or they would have had it on the pocket guide. So that's why we picked this as B. Just suppose you had a flash point and it was maybe 230 degrees F. You'd say, well, that's a D, but you always pick the lowest letter. So it doesn't really matter. Even if it was under 100 here, that would still be a B. There's no A. So this is definitely a B. Now we do step 2, where we determine the rate of contaminant evolution. We are still using table 6.2 for this part. This is the top and this is the bottom of that table. It's like 2 tables in one. We have T equal 175 degrees F, and T boiling is 225 degrees F. And what it wants is the difference. So delta T equal 50 degrees F. The delta T below boiling. The liquid temperature was 175, this row, and the degrees below boiling we just calculated was 50. So we look at this next column, and 21 to 50, this one happens to be on the border here. We're going to call that 2. Evaporation time we don't have, and we don't have anything about gassing. So I'm going to call this 2, so B2 is our class for this particular chemical at these temperatures. Step 3 was to determine the control velocity. Once we have the class, we just look this up, find our B2. We're talking about a lateral hood. So our control velocity is 100 feet per minute. Step 4, we calculate this required Q. So we're going to calculate Q over A, then Q. So let's look at table 6.4. Now we worry about which tank it is. Case A was a tank against the wall, lateral exhaust on one side. Case B was freestanding tank, lateral exhaust on both sides. So we're going to consider both of these. We'll do A first. This is case A. So we're using this set of numbers. Our control velocity was 100. And now we have to calculate the aspect ratio for a tank against the wall. The aspect ratio is equal to W over L, which in our case turns out to be 0.3 based on the numbers that we have. That is at this range. And so we find this 150. What is that 150? Q over A is 150 in units of feet per minute. Now we can finally calculate Q. Q is equal to Q over A times A is equal to 150 feet per minute times 10 feet times 3 feet, L and W. And this gives me 4,500 feet cubed per minute. So this is my answer for case A. Now we need to work on case B. We still have the same control velocity 100 FPM as before. We don't have to repeat all that because it's the same temperature, same boiling temperature, same PEL, all that stuff. It's still the same class and everything. When you get to step 4, table 6.4, we have to be careful. See footnote 1. This is a lateral freestanding tank, lateral hood on both sides. A freestanding tank like this with a lateral hood on both sides. So you're drawing out air like this, and we have some liquid in here that's evaporating. And so what happens is if it's double like that, the air is going to be coming in like this, symmetrically about the center line. And so if you think about it, kind of ignore the left part, this is like a lateral hood against a wall. And so if we look at footnote number 1, it says use half of the width to compute W over L when it's on both sides of the tank for a freestanding tank. This is this footnote 1. So we have a freestanding tank like that, and that footnote 1 applies then. And what they're really doing is saying this is like a lateral hood against the wall, where this is kind of your wall here, and that's your W over 2 instead of W. So the only thing different we have to do here is we say W over 2 over L is the aspect ratio. And so that turns out to be 3 divided by 2 over 10 equal 0.15. So we're going to use this instead of 0.3. So in table 6.4, our aspect ratio is in this range, 0.15. Now we have a freestanding tank with a control velocity of 100. So we go down here and find 175. So now we have Q over A is equal to 175 feet per minute. And then when you multiply by the area, you get Q equal 5,300 CFM for case B. This is the total on both sides since I used the total area. And so case A is better because it has less Q.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.